This webinar is sponsored by NEC Corporation, a $37 billion technology leader with over 100 years of innovation. Their ProgrammableFlow network suite was the first commercially available enterprise-class SDN solution to leverage the OpenFlow protocol. Thank you for your time and interest in NEC's ProgrammableFlow network suite.
This sponsored webinar is one of many IP Space Data Center webinars. You can register for live sessions, buy the recordings, or get access to all of them with a yearly subscription. For more information, visit ipspace.net/dc. We all know that, we build whatever physical topology we build, and we have whatever hypervisor solutions and virtual machines and so on. But what the customers actually want is something like this. Most applications today rely on pretty complex application stacks with multiple tiers that are linked together with layer 2 segments, routers, load balancers, and firewalls. And we have to emulate that somehow in the whatever virtual networking solution we are proposing. And this is how NEC is doing it. Their major concept are virtual tenant networks. And a virtual tenant network is an isolated network that is built logically for individual tenants. And the tenant doesn't care about the physical infrastructure in the network. So that's why there are the clouds there. And the person configuring the virtual tenant network doesn't care about the physical topology in the network. So when you configure this virtual tenant network, you don't care about VLANs, at least not in the core. You don't care about trunking. You don't care about allowed VLANs. You don't care about spanning tree. You don't care about the core network at all. The only thing you're really interested in is how will I connect the tenant endpoints together. And there are two types of nodes you can have in a virtual tenant network: the bridges and the routers. They're all virtual, remember. This does not map into any physical device. This is a conceptual model that is used to calculate the flows that then have to be downloaded into individual devices. And by the way, the virtual routers can do IPv4 and IPv6, which, by the way, I think is more or less one of the first virtual networking products with full IPv6 support. Now, all these nodes have virtual interfaces. You have virtual bridge interfaces on the bridge, virtual router interfaces on the router, and external interfaces on the edges of the network. And finally, you have to add the virtual links that connect all of them together. And then you have to somehow map these edge interfaces to physical ports. And you could very easily say, I have this physical port, let's say on which a bare metal server is configured or a firewall is connected to it, and it maps straight into a virtual layer 2 segment. Or you could have another device here that has multiple VLANs on this trunk link, but the trunk link is a physical concept. We don't want to know about physical networking here. We are talking about virtual networks. What we need here is we are mapping a certain VLAN on a physical port to a virtual segment. And even though each virtual segment is associated with a VLAN, because internally we still need some identifier and VLAN is just convenient, we can do VLAN rewriting on the fly. So you could say I have VLAN 1 here on this particular link, but by the way, internally this is VLAN 1000. So we would use this manual mapping for external physical devices where you're not using any VLAN tagging with the external device, or in the case of overlapping VLANs. If you have the well-designed network in place where the VLANs are the same all over the place and trunking works as expected, then it's way easier to say, okay, you know what, I just have VLAN 100 in this segment, and whatever appears with VLAN 100 from anywhere in the network belongs to this segment. So this simplifies the configuration. And with this, every external port that you configure that can participate in this particular logical segment can automatically belong to that segment. And the VLAN membership has to be configured manually. So the trunk links have to be configured manually on the external ports with the prior software release. And now with PF1000, because we are controlling the whole thing, you automatically configure the VLAN membership with Hyper-V. And then there is the expanded VLAN mode, where we are still using VLANs, but VLANs only have local significance. So they are not the same end-to-end, but on an individual physical switch, you might have VLAN 100, but on another physical switch, you have VLAN 200, and it would be the same virtual segment. So you would use the expanded VLAN mode when you have overlapping VLANs. So for example, you have some traditional data center switches from some other vendor, and they only support 256 VLANs, and you need more. So you would have overlapping VLANs. You can solve that with expanded VLAN mode. Or if you need more than 1,000 vBridges, so if you need more than 1,000 VLAN IDs in the whole fabric, then you have to go for expanded VLAN mode. And then there's time to map these logical segments to the physical world. Remember, the bridges and routers, they don't exist in the physical devices. So although it looks like this thing here maps perfectly into this thing here, there is actually no match between the two. It's not like the edge switches would be layer 2 switches and the core switches would be layer 3 switches. This virtual network is mapped on the physical topology, as I explained before, in an optimal manner where the ingress edge switch does most of the heavy lifting on the external port, including things like MAC header rewrites for routing and TTL decrement for routing. So even though the virtual network looks like this, actually the whole functionality of a bridge, a router, and another bridge is implemented on the edge switch and downloaded from PFC as flow entries into this edge switch. So the packet forwarding across the network is always optimal. If you have two devices connected to the same physical switch, and even though they are in two different layer 3 segments, the packets will always flow optimally. And because TTL decrement is implemented, even traceroute works across virtual routers, even though virtual routers don't exist anywhere. Talking about the control plane, these things are still pretty simple. So on the bridging side, we have the MAC address learning plus static MAC addresses and MAC table aging. And on the routing side, we have IPv4 and IPv6 subnets with associated ARP and ND learning plus static entries. And we have static routes. No routing protocols yet. We do have DHCP relays, so if you want to use DHCP on the end nodes and the DHCP server is somewhere over here, the virtual router can do DHCP relaying. And then there are packet filters. On every single interface in the system, on every one of them, you can apply a packet filter, inbound or outbound. And these packet filters can do permit, drop, or interestingly, redirect. And remember, you can apply the packet filter here on the virtual router, but in reality, the packet filter would be applied on the ingress port on this switch. So whatever you specify, wherever you configure the packet filters, they are usually implemented on the ingress port of the ingress edge switch. The configuration syntax is very similar to what Junos has or what Cisco IOS has with modular quality of service CLI. First, you have a flow list that specifies the traffic matches, and then you have the filter list, which specifies which actions are applied to a particular type of matched traffic. And you can match on the expected things: MAC source destination address, ether type priority, and IPv4 and v6 source destination and port numbers. So you cannot build a real virtual firewall with this, but you can build access lists or packet filters. And here is a sample configuration syntax. we have a flow list which matches certain destination IP address, and we apply this on a particular interface on the bridge. Flow filter in, so this would be applied here. And if the packets from this host have this destination address, then we pass the packets, otherwise we drop them. A really interesting option is traffic redirection. Instead of dropping the packets, we can redirect the packets to some other device. For example, you might have a web proxy here, and in this case, we would match all traffic going to port 80, coming to this port with destination port 80, which means that this particular host is doing some HTTP requests to an external web server. And we can redirect this packets to, let's say, transparent web proxy. But now the problem we have is that this transparent web proxy has its own MAC address, and it's only listening to its own MAC address. So we need to rewrite the destination MAC address to match the MAC address of the web proxy. And this is how we would do it. After this, all TCP packets going to TCP port 80 coming from this host would automatically land at the transparent web proxy. And you know what the use cases are. Either web proxies, as I already mentioned, or IPS or IDS, or even some baseline load balancing functionality. Thus, layer 2 and layer 3 address make sense in OpenFlow networks. Well, actually, what we have to do is we have to map the traditional networking concepts into this virtual tenant network so that we can figure out how to forward the packets. So from the pure OpenFlow perspective, we're actually matching on values in individual fields in the packet. So an OpenFlow switch doesn't care about layer 2 or layer 3 addresses, but the end user does. And so yes, layer 2 and layer 3 addresses make sense from the virtual tenant network perspective. Can PFC program virtual firewall functionality? Well, not stateful. Stateless packet filters, yes. Stateful, no. How do I integrate the vRouter with external routers through dynamic routing protocols, etc.? You can't. At the moment, it only works with static routes. Does VTN deals with the resource sharing? If you mean link sharing, then absolutely yes. As I explained, the virtual tenant network is just a concept used by the controller to figure out what's going on. The controller then figures out what the best path is across the network and then installs the flow entries as granular or as generic as they need to be into the individual switches. So yes, it absolutely takes care about the resource sharing. What actually happens when controllers are lost, for example, from a bug? So if PFCs share memory, they could stop working together. Would the network still work?
If there is any such corruption or it goes into a wrong state, the switches can only work up till the floatables expire. But if it goes into a wrong state and it cannot create new floatables, then all the future flows will not be created. So it gives you maybe a little bit of time to restart or take it to the right stage.
So as long as the topology doesn't change, we are good, and we hope that the controller restarts in that time. What about the firmware upgrades to the PFC?
The version upgrade into the PFC or the controller actually can be done in a way where you do not have to have any interruption into the whole network. It is basically done by using the whole active standby, so where we make the standby primary and upgrade it and then take it to the next stage. So we have a totally non-interruption based migration path from one version to the other version in the network.
So a follow-up question to the previous one, will the network continue working as long as the topology doesn't change or as long as the MAC addresses don't age out? I would say whatever is first.
That's correct.
This is an interesting one. Do the program flows age and expire after certain timeout or only when they are reprogrammed from the controller?
It expires. There is an expiry timer, and you can set it to different values. But typically for robustness and also to ensure that the floatable size doesn't expire, the typical way is that you keep it for around 10 minutes or even 1 minute after there is no packet flow going on there. So if there is any flow which is idling for some period of time, then it automatically expires until a new traffic comes in where the controller goes and adds that flow table into each of the switches.
Another question, what about VLAN stacking or Q-in-Q? Can you use VLAN stacking on the edge ports, for example?
Typically, switches provide that, but there isn't a functionality which can be driven by the controller at this point of time.
How to manage loops if the virtual topology of the VTN has redundant layer 2 paths? Can you have like 2 virtual routers in the virtual tenant network?
No, you cannot have more than one virtual router, because essentially a single virtual router is enough to declare your requirement in terms of how many subnets you want. And if you look at it, it's a very much like a tree type of way of defining. So you cannot actually create a loop in that VTN design of it.
If you have questions after watching this video, send a tweet to @iOSHints or send me an email using contact form on ibspace.net, where you'll also find information about other data center webinars. For all commercial questions and programmable flow evaluation requests, please contact NEC.